you. So some of you had some discussions about these, but in any case, is there a time delay? All right. No time delay. The answer is no. I mean, I think the main difficulty in here is that one is actually said to be, I mean, this action reaction, these particular words actually confuses a lot of people. So when you say action reaction, some people think that, well, action is applied first, and then this somehow causes something, some kind of events that causes the reaction to occur. So as a result, the reaction should come later. No, this is not about this kind of a thing. So it basically says that for this force to exist, the other force should also exist as well, right? That's basically some kind of a necessity. It's like having a money with two sides. You cannot talk about one side of the money without the other side being present, right? It's some kind of a logical necessity, right? Just keep in mind that everything is basically the interaction, and two objects are interacting. As long as they are interacting, there are forces on each one, and each one is non-zero. Okay, so I don't know. Some people have these kind of confusions as well. So, for example, when you put a box on the floor, for example, we know that there is a gravitational force on it, and we also know that there is a normal force applied by the ground on this one. And well, if it is at rest, then these are going to be the same. Some people call these as the action-reaction pairs. Well, it isn't, right? So somehow, I don't know how the thinking goes, but the misconception is that somehow, because of the fact that there is a gravitational force on it, because of that, all right, there has to be, eventually there has to be a normal force developed later, right? So as a result, they think that, well, there's some kind of a relationship between them. No, it isn't, right? This gravitational force is basically applied by the Earth. So as a result, on the Earth, there has to be a force, equal and opposite force applied on it. And this normal force is basically applied by the ground. So therefore, this is applying a force on the ground. So as a result, there are these action-reaction pairs, but these are different from each other. Okay, so for the case of two charges acting forces on each other, so that's the Coulomb force. So these two forces have to be the same because they have the same expression, right? What is it? Q1, Q2 divided by R squared. So this has the same expression as well. So these forces are always the same at all times. There's some kind of a situation where when these things are moving, and so as a result, you have to think about this electromagnetic field in here, in which case you have to consider this field as a third object, third entity. And this third entity is applying forces on these charges. In this case, of course, we're talking about something else, okay? I think the electron should wait for the photon to come out. Forget about these kind of explanations. So these are some kind of explanations that people use to explain some mathematics of quantum electrodynamics. You shouldn't actually understand them literally like these. Okay, so there is no time delay. Excuse me?
May I ask something?
Yeah.
When it comes to gravity.
What?
When it comes to gravity,
yes.
You know, let's say that the sun is vanished. Now,
yes. Yes.
Will we feel the loss of this gravitation
later?
Instantly,
yes.
Or later?
Yes.
Later?
Yes.
8 minutes later, right? Because
yes.
of the speed of light. Yeah, okay.
Yeah, the reason is, well, I mean, what's important in there is that it's not the sun that's directly applying a force on the Earth. but
Yes, not a physical
it's
force.
the
Yes,
it's the
I see.
medium itself, right?
Yes.
So you have to think about the medium in there, right? So there's a different physical entity, just like the electromagnetic field in there. So these are kind of complicated issues, but think of it as the, I mean, the paper thing, right? Two sides of a paper, right? You cannot say that, well, first this side is created, then after this side is created, with some delay, the other side is created. No, right? Whenever you produce this paper, both sides are present at the same time, right? It's just a logical necessity. Okay. The second one too, it's basically an interaction. So only two objects can interact. Right? It's basically an interaction. An object cannot interact with itself without the presence of another object, right? That's not possible. And so as a result, this is also no. Okay, only if there's a second object, there can be an interaction. Interaction is meaningful only with this. And the force is basically as a result of interaction. So there has to be a second object which applies the force. That is necessary. So there cannot be any kind of a situation like that. Nobody can apply a force on itself, right? That's other thing that we say. So, of course, at some point we also say that there are four mechanisms of applying forces. Okay, so one is gravitational. You know these. Second one is electromagnetic. So this is something that we are going to see in the second semester, electromagnetic. And then there is this weak force and strong force. I'll describe all of these basically. We won't be able to see these, but most of the forces, except the weight force that we will see in the semester, all the other forces that we are going to see in the semester is electromagnetic in origin. So it's basically the interaction between the electrons of objects that are interacting with each other. So in any case, these are mechanisms of interaction where the particles interact with other particles. So in each case, there are two objects, two particles that apply these forces to each other. So there is no way that nothing can apply some force to a particle. What is U in this case? No particle can apply a force on itself. I mean, it's basically this thing which is stated in a different way. So nothing cannot apply a force on a particle, or nothing cannot apply a force on a particle. That's one statement that I have written in here. The other statement is that a particle cannot apply a force on itself. Both of these are actually forbidden by Newton's third law. Okay, so let's quickly go ahead with the definition. So we are still with the definition. So we know we have learned about the gravitational force before, right? We have talked about this. We just talked about the free fall motion after that, right? So the name of the force is called the weight. I didn't talk about the units. I'll talk about the units as well. The gravitational force. So it's called the weight. The force itself is called the weight. So therefore, it's a vector quantity if you want. But sometimes the scalar magnitude would also be called as weight. Again, in everyday language, people use weight and mass to mean the same thing, but as physicists, we are not using this everyday language here, right? So whenever we say weight, it's always the force. Just keep this in mind. So how do I find the expression for that force? Oh, we just look at the free fall situation. So we know that in a free fall situation, an object has this acceleration, which is equal to the gravity. And since this is the only force, I know that the weight force acting on it should be equal to mass times the acceleration, which is equal to the gravity. And so therefore, we find the expression of the weight force like that, okay? So later when we see the gravitation chapter, we are going to understand why this is the case. All right, so therefore, we just write down this expression. So I think I have a statement about the third law in here. So again, this is the object in here with mass m. We know that if the gravity in here is equal to g, the gravity is g, the weight force on this object is equal to m times g. All right, that's what I have said before. So what's the third law pair on which force is acting on which object in this case for the yeah, the third law says that there's a second force, and what is that force and what's acting on it? Whatever. So that force is basically acting on the Earth. We usually assume that this is acting at the center, so we will explain the meaning of that location later in a different chapter. So in any case, so this force must be equal and opposite, so therefore that force should be minus m times g. But just keep in mind that g in here is the gravity at that point. It's not the gravity at the center of the Earth. In any case, this is because of the third law in here. So Earth is pulling us with that force, with that magnitude. And so therefore, we also pull the Earth towards ourselves with a force in the upward direction with that magnitude. It doesn't matter whether we are in free fall or not, right? I mean, this is the force, this is the gravitational force between the Earth and ourselves. Okay, so it doesn't matter what this thing is doing. It's in free fall or it's resting on a table, doesn't matter. So there are some other forces acting on the Earth as well. But in any case, just keep in mind that the Earth is also accelerating because of these forces, the center of the Earth. But when you compute the accelerations, this becomes an extremely tiny quantity. Okay, so let's say the units. Let's say units of force. So I needed to mention about this. So because of F equals m times acceleration, the unit is basically kilogram meters per second squared. We just call this as Newton unit and show this with capital N letter. Okay, let me quickly go ahead and because I need to describe something else as well. All right. This is the gravitational force. This is third law. Yeah, the contact force between two objects which are in contact with each other. Okay. So what happens in here is this. All right, first the explanation. Why do two objects in contact apply forces to each other? Because at the interface in here, I'm just going to magnify that interface region. So let me magnify it like this. Okay. At the interface in here, there are atoms on both sides, and each atom has like nuclei and electrons and whatever. It's not whatever, so it's just nuclei and electrons, right? So there are these atoms in here. So we know that these charges apply some forces to each other. These are electric forces in here. So basically, the electrons push away each other. So that's the Coulomb force. It's also possible that these electrons attract the nuclei. So there are also these attractive forces as well. But somehow, the repulsive forces between the electrons somehow dominate because the electrons are more outside, so they are actually much closer to each other. Okay, so that's basically the reason for the force between these two objects. Okay, so therefore there's some kind of a force acting on these two objects, Otherwise, if there is no force, then these two objects will basically enter into each other, which is something that we don't observe. But in any case, we can understand the existence of that force because of that reason. They don't somehow enter into each other. Unless one is a dark matter, in which case there is no force between them, in which case they can enter into each other. So, I mean, this is some just extra information. So probably, for example, dark matter might be actually passing inside us. We don't observe them because we don't interact with them, right? So as a result, it is possible that two objects can pass inside each other if there is no force possible between their particles. So that might be the situation with the dark matter and normal ordinary matter interaction. But if it is two different matter, matter is always formed from protons and electrons and atoms and things like that. Two matter basically interact with each other when they are close enough because of this Coulomb interaction between them. And that's why they don't enter, they don't pass inside each other. So as a result, if they are sufficiently close, they apply these forces to each other. I just call them as contact forces. Okay, so here is the detail, right? Since this is something that we use a lot in solving problems, we just name the components of these two forces with different names. There is this component of that contact force perpendicular to the surface. Let me say it like this. Let me not say component, but let me just say that it's the projection of that contact force in this perpendicular direction. So that's the normal force. It's called the normal force. It's just a component of the contact force, actually. So let me say it like this. This is the perpendicular part of contact force. Okay, it's not a good description in any case. So there's this part of the contact force which is parallel to the surface, and that's called the friction, right? We just define the friction like that. So therefore, I mean, we somehow define some kind of an interface, which we are going to assume to be a plane. The component, the part of that force which is parallel to the surface, we just call the friction force. All right, and then we'll talk about the friction laws later. So that's the parallel part. I mean, parallel to the surface, all right? Obviously, of course, the contact force is really is the sum of the normal force and the friction force. Okay, all right. In both cases, obviously, there's a reaction in here. So how do I show this? I'm going to use this blue color in here. So if B is applying on this contact force, there is a contact force applied on B as well. So that's minus F contact in here. In any case, I can basically do the same thing for the normal and the friction components. So for the normal force, there is actually because of the third law, there is a force applied on the object B in here, and there's also a friction applied on object B as well. Right? Yeah, whatever. I mean, there are these action-reaction pairs of these forces acting on this one as well. Then how there's ask these questions later, right? So the tension in a string. So that's also something that we are going to meet a lot. I would like to clarify this thing. So that might also be confusing to you. So we have a string like that. Usually I'm going to assume that it is tight. In that case, right? I mean, I'm talking about this string in here, right? So let me magnify this part of the string in here. So that's the magnified thing. Right? This is the magnified picture. So that's the string. Right? That's the string. Okay. What we do is we mentally divide the string into these two parts. At any point we want, I can somehow think about some kind of a plane that's dividing these. So it's like a mental division in here. And call one part of the string as A, the other part as B, all right? But specifically, I'm talking about the atoms on this part, atoms and electrons on that part, and atoms and electrons, yeah, whatever, electrons and nuclei, the atoms on the other part, right? So there's a chemical bond between them, and chemical bond is basically electromagnetic. So therefore, because of some reason, they apply some attractive forces to each other, right? Again, this is an electromagnetic force. They apply some attractive forces to each other, okay? In any case, as a result, the total of that force is basically is the tension force. But on the, I mean, it's basically an attractive force. So this A part, for example, is pulling the B part in the upward direction. And the B part is pulling the A part in the downward direction because of that, right? Again, because of the action reaction, these two forces must be equal to each other in magnitude. Okay. So when we say tension, we talk about this magnitude of that force. The tension force, right? There is a force, but it's a force between these two parts actually. So when we say tension, we're not talking about a force applied on a definite side, because there are these two sides in here, parts A and B. The magnitude of that force is called the tension. So therefore, this T in here is a scalar. It's just a number only. We just give the value of the tension, okay? But the actual force is a vector, obviously. So if I want to talk about the force on A, so let's say it like this. Let's say force on, I think this part was B. Again, applied by, sorry about that. So this is the force applied on B by A. It's equal to that tension multiplied with some unit vector that shows the direction along that direction. So usually, you know, the orientation of the string. So as a result, you can easily find that direction. And so as a result, you can easily deduce what the force is, but usually we just deal with the magnitude in here. So as a result, whenever we say tension, the tension is always a scalar quantity. So as a result, when I ask you to find the tension in here, you just need to write down the numerical value of the tension, okay? Just keep this in mind, it's just some kind of an exceptional thing. Okay, that's it. So we have spent 2 hours without doing anything. So sorry about this. So let's then start solving some problems. So I'm going to solve some problems, but let me first think about things. Okay, I'm just going to start with the incline problem. You know the solution of this thing, but I'm going to solve it in any case, but I'll just illustrate some of the concepts in here. So we have some kind of a block in here. There is no friction in here. Sorry about that. No friction. There's an incline angle in here, and we would like to find the acceleration of the block. I'm going to solve a similar kind of a problem with the same geometry in a moment. I think I'm going to do this, but first let's just clarify what we do, right? So the first step is, the very first step is to draw what we call as free body diagram. Right? Basically a picture where all forces acting on each body, right? Let's say show all forces on each body separately. All right, that's one of the problems that people face. They don't usually separate the bodies, and somehow people usually draw these free body diagrams on the same thing, but separate each one of them so that you just consider each object in here separately. So for this one, for example, let me just do it like that, right? So I am just going to do this, right? So let me also show the geometry in here. So that angle is theta. Okay. So what I do is I just show each force in here separately. So as a result, one of them is the gravitational force, right? And the other one is the normal force. For the normal force, I'm just going to use the little n symbol. And so as a result, I'm just going to show it like that, right? So that's the correct free body diagram. Okay, so there are incorrect, so that's the correct. Let me say free body diagram, all right? But there are incorrect ones, like this one. So let me squeeze it in here. So the first one is this, that we meet a lot. mg cosine theta, mg sine theta. All right, that's incorrect. Why is it, let me say incorrect. Why is it incorrect? Because you're just writing down the components of this gravitational force in here. You're not writing down the, the force itself. So, I mean, at this point, you're kind of assuming that you have started solving it, but this is the very first step. So in the second step, we need to start solving things. So as a result, do the things correctly. So in the first instance, just draw the forces in the usual directions, all right? So that's going to be less confusing, and you should be able to understand some of the important issues later, like the action-reaction pairs, for example, if there is a second body. So you will get less confused by that way, all right? Just draw the ordinary force. Do the decomposition later, right? In the first instance, just draw the forces only, okay? Just keep this in mind, because that will actually make things simpler, all right? The second one, there are many things that can go wrong. A lot of students do this. They just write down the solution before even starting solution. Again, incorrect in here. So I'll actually give you the reason later, incorrect. Don't start solving yet. Because to be able to solve, we have to first write down some equations, and then after that we start solving. Don't start solving at the very beginning. Okay. So as a result, I mean, this is basically incorrect. So you should basically just write down a label that tells us the nature of that force. And in some cases, who is applying that force, right? In this case, it's obvious this incline is applying, but because of that, we don't say anything further in here, but in some cases, this might be necessary. What else? It's the third one. So let's say that sometimes we also need to show the force on an incline. Okay. People show it like that. All right, so that's also incorrect. Sorry about this. Again, incorrect. So in a free body, let me say that this is not free, right? Force on the incline is shown. All right, but we're basically showing the forces on the block only, right? So as a result, this should not be in here. What else? Yeah, I'm also going to do this, right? So, I mean, this is not common, but in some certain kinds of problems, people also do this. They just draw m times acceleration in the upward direction. Again, this is not a force, right? This is not a force. In any case, I mean, these are some kind of mistakes that actually I used to see in during the times there were like written exams. You won't make these kind of distinctions on an online exam, but still I need to talk about these kind of things because these are things that you actually start learning in high school. And sometimes you start learning without understanding the main reason. I mean, there might be some kind of reasoning behind them, but you have to understand clearly what the reason is, right? So in any case, let's just go back to the beginning, the first one, right? So there's no frictional force in here. So this kind of shows all the forces in here. We also know who is applying these forces. This is applied by the Earth, the center of the Earth, actually, if you want. And this is applied by the incline. So as a result of that, this thing has an acceleration, and usually to distinguish the acceleration from the forces, I show the direction of the acceleration. Like that, right? This is my convention, all right? Nobody else is actually applying these. It's taking so much time to solve this simple problem, but it is necessary. So there's one more thing. I'm sorry about that. There is one more thing, right? I'm just going to look at this one. So what does that mean, right? I'll explain this, right? Whenever I do this, right? I mean, whenever I draw an arrow and write a scalar symbol next to an arrow, I actually mean that n is the component of the vector n along the direction of the arrow. Right? Component is a scalar, so this symbol is just a scalar symbol, right? I actually mean that n is the component of a vector quantity along the direction that's shown in here, which means I can show the same thing by using an opposite arrow. So if I choose the arrow in the opposite direction, then the component would be minus n. Okay, so I'm going to use this convention, and a lot of people actually use this convention, which is quite nice because in some cases, it simplifies the solution of the problem. In some cases, for example, you may not know the actual direction of the force or actual direction of the acceleration. And so as a result, this convention is extremely useful. So please keep this in mind, all right? So at the first problems, perhaps this may not be necessary, but that's the convention that I'm going to use. But just distinguish this from this convention. If I put a vector symbol in here, it just means that n is a vector. Okay, so I'm not going to use that kind of a convention if I use a vector symbol in there. So no convention in here. No convention in here. Okay. But whenever I use this kind of a thing, whenever I use a scalar label, it always means a convention. So in the past, I have made some mistakes with this rule. So as a result, just ignore these. But in the future, I'm going to use this consistently, okay? So all of these, for example, this A is actually the component of the actual acceleration vector along that direction. Okay. All right, so let's then go ahead and then solve this problem. All right, let me redraw again free body diagram. And then I have this acceleration in here. So what I do is in the second step, write Newton's second law. All right, so basically, net force is equal to mass times acceleration. I need to apply this for each object, basically. And in that case, net force is basically the sum of these two forces. Yeah, I think I'm going to give a break, but let me give the essential things in here. In any case, I don't want to do vector algebra. So as a result, I don't want to use unit vector notation and things like that. So what I do is, I just write down this equation in component form. So as a result, I'm just going to do it like this. So I'm just going to write down the x components and set it equal to the x component of the acceleration, and write down the sum of the y components of the forces and set it to equal to the mass times the y component of the acceleration. Okay, that is what I am doing. All right, in all cases, I will be writing down the components of the forces on the left-hand side and components of the accelerations on the right-hand side. In some cases, these components will be zero, and I won't write anything there, but actually, I mean, all of the forces have components appearing on the left side, all right? Just keep this in mind. However, I have forgotten something. I need to establish a reference frame before writing them down, all right? To be able to write down the components in here, I have to use a reference frame. And in that case, there's a choice involved. How do I choose the reference frame? Should I choose it like that? That's possible. I can choose it like that. That's a possible choice. Or should I choose it like this? The place of the origin is not important in here. So as a result, the directions of the axes are a little bit more crucial. Or should I choose it like that? I don't know, some other directions perhaps. Answer is each one is valid, right? For each one, you can write these equations and they will be valid equations. They will have the same solutions. But usually, one of them is better than the other ones. And for this problem, for example, this reference frame is better. And that's why we usually pick them, okay? So in the solution of these kind of problems, it's always the case that we use a reference frame, we choose some axes, and when we have, for these kind of vector equations, we just write down the components of these vectors, all right? That's what we are doing, okay? So as a result, even before the second step, we have to do this choice of the reference frame handled first, all right? Just keep this in mind. So in this special case, for example, x component of the normal force is 0, the y component is n, as I have said in the free body diagram. For the weight force, the x component is equal to mg times sine theta. Yeah, in that case, I have to just show that angle in here. And its y component is equal to minus mg times cosine theta. And for the acceleration, acceleration has an x component, which is a, and its y component is equal to 0. Okay, So as a result, I mean, we are basically decomposing each force in here. So as a result, yeah, let me quickly do this. But in the on Monday, I'll just I think I'm going to go over this thing and write down the solution. Or let me just do the solution. So along the x direction, the n has 0 component. So this has a component mg sine theta. And the acceleration has an x component, which I have called as a in here. Okay. Along the y direction, the y component of the normal force is n. Y component of the weight force is minus mg cosine theta. And the y component of the acceleration is 0. So what's important in here is that I'm not subtracting the vectors on the left-hand side. I'm adding them, but I'm adding the components, and some components are negative, right? So that's important, I think. So let me quickly then write down the solution. So therefore, we find the acceleration to be equal to g times sine theta, and the normal force to be equal to mg times cosine theta. Okay. So what's important in here is that, I mean, these are the results of the solution. There were 2 unknowns in the problem, and we had 2 equations. By solving these 2 equations, we have solved for the 2 unknowns. Acceleration is a vector along the, which is parallel to the incline. So therefore, it's along the x direction. So therefore, the y component of the acceleration is 0. Yes, I'm writing this equation. Basically, I'm writing the components of that equation. But usually, I'm not going to solve these problems with these kind of things, steps, because, well, this is too long. Yeah, I mean, I'll be just directly writing n minus mg cosine theta is equal to 0, for example, as most of you actually do. But in the first place that we mentioned that, let me just stress on the fact that we are writing down the components of the vectors in there. And some vectors, even though they are non-zero, might have 0 components along these directions. Y is perpendicular to the direction of the motion, yes. Okay, so let me stop here. If you have further questions, then you can ask me during the break.